is going to give our short talk. I just wanted to also let you know, as Diane mentioned, we are accepting, in fact begging for images for the Warren Astronomical Society calendar for next year. Mostly we look for astrophotography, but we consider interesting sky photos with an astronomical bent included, and nice shots of Stargate are always welcome.
Who should we send those to?
You can send them to calendar@warrenastro.org, or you can send them to filters. So.
I think Ken needs very little introduction. He has been a member of this club since the 1970s. He's been our vice president and president. He's into, are you still into going to eclipses?
Absolutely.
Absolutely. He frequently has given us presentations on famous astronomers, and he gives the in the news presentations. He's been awarded the John Searles Award and lifetime membership in this society. Tonight, the history of the telescope up close and personalized.
Part 2. All right, we gave a presentation on this a while back on the early part of the observational telescopes, and this gives a little bit more personalized view of it, and I will try and run through this as quickly as possible. I certainly will stay within the time limit, which I know that Jonathan will thrilled about. All right. Okay. Let's talk about a couple of them. First of all, we got the Hubble, the Corot, and the Kepler. All three of these scopes have performed amazing feats of research. The Hubble is a 94-inch scope, which had its difficulties focusing when launched in 1990. The mission from the shuttle fixed it, as you can see, and in 1993. Corot was launched in 2006 by the European Space Agency, and Kepler was launched in 2009 by NASA and searched for extrasolar planets and added over 3,000 candidates to date. Well, there's one other one we wanted to hand on the, other than just optical telescopes. There is a vast array of telescopes dealing with other wavelengths that have been created, and I won't take much time with this one, so like the others for no particular reason other than time. In 1931, Carl Jansky discovered that astronomy objects give off radio emissions. After World War II, a new era of astronomical observatory began dealing with other parts of the electromagnetic spectrum, all the way from radio to gamma rays. Jansky discovered the radio emissions while performing research in terrestrial static with a directional antenna. He was born in Oklahoma while still in the territory. His father was Cyril Jansky, Dean of College of Engineering, University of Oklahoma, Norman. Carl attended college at the University of Wisconsin. Madison received a BS in physics in 1927. Joined Bell Laboratories the next year and was assigned to investigate atmospheric kinetics property during short wavelengths of about 10 to 20 meters. Jansky's specific job was to investigate sources of static that might interfere with radio voice transmissions. Sometimes called Jansky's merry-go-round, the antenna was built at a diameter of 100 feet, stood 20 feet tall. We also have Rober, who also worked with him at that point in time. And Rober built a more sophisticated radio telescope in 1937 and discovered various unexplained radio sources. And of course, as we went there, the larger discs, as they were Arecibo, Episburg, John Brown, and Green Bank, obviously. Infrared telescopes. Infrared astronomy came soon into being in the 1960s, starting with balloons and moving to planets and rockets. NASA's Stratospheric Observatory with infrared astronomy, SOFIA, was put to use in 2010. The first space-based infrared telescope was an infrared astronomical satellite launched in 1983. The Spitzer infrared space telescope was launched in 2003. And of course, the Wide Field Infrared Survey Explorer WISE was then launched in of course, 2009. Ultraviolet telescopes appear to resemble optical telescopes, however, Conventional aluminum coated mirrors cannot be used, so alternative coatings such as magnesium fluoride and lithium fluoride are used with them. The ultraviolet telescopes were again developed in the 1960s. The orbiting solar observatory satellite carried out observations in ultraviolet light as early as 1962. The International Ultraviolet Explorer surveyed the sky for 18 years using an 18-inch aperture telescope with 2 spectroscopes. And the Extreme Ultraviolet Explorer, launched in 1992, was a satellite that operated at these wavelengths for a 9-year mission. X-ray telescopes from space do not reach the surface, so all X-rays astronomy must be conducted outside the Earth's atmosphere. Suborbital flights were used in 1948 to first detect the X-rays from the sun and as a residual force X-rays from galaxies and nebulae. The first detected were the Scorpius X1 and the Crab Nebula in 1962. Several scopes were used before the first dedicated X-ray telescope, which was launched in 1970. 300 sources were discovered by the Lulu, Exosat, Rosat, Chandra, and Newton were successors launched. The study of gamma rays was started in early in the 1960s, a balloon-borne experiment with the launch of the OSO-3 satellite in 1967. Gamma ray astronomy really got its kickstart. The first dedicated gamma ray satellites for SASB and COSB. The Compton Gamma Ray Observatory was a technological leap from the earlier satellites. Very high energy gamma rays can be detected from the ground via the Cherenkov radiation, named from Pavel Cherenkov, who first discovered it in 1958, which he earned a Nobel Prize for physics. Cherenkov radiation is produced by the passage of gamma rays in the Earth's atmosphere, which led to the Hegra, Stacy, Hess, Magic observatories. Star Trek creator Pavel Chekhov was a tongue-in-cheek name for him, by the way. It was named for him. Sputnik and Cherenkov collector. Infrarometric telescopes were developed when French physicist Hippolyte Fizeau who was first to propose the use of the array of small telescopes to measure the diameter of a star with the same precision as a single telescope, which was larger than the whole array, a technique which later became known as astronomical interferometry. In 1891, Albert A. Michelson, first to accurately measure the speed of light, successfully used the technique for the measurement of astronomical angular diameters for the moons of Jupiter. It took another 30 years for direct interferometer measurement of stellar distances, and Betelgeuse was first, by the way, when a 20-foot interferometer was mounted on the 100-inch hooker by Michelson and Francis G. Pease, who was assisted by George Ritchie and Yerkes, and discovered the first planetary nebula within a globular cluster when a 20-foot interferometer was mounted on the 100-inch hooker telescope. In 1946, Martin Rye, the Nobel Prize winner in 1974 and 12th astronomer warrior, and Derek Von located in a number of new cosmic radio sources by constructing a radio analog of Michelson interferometer. Signals from 2 radio antennas were added electronically to produce interference. With the development of larger arrays, which could rapidly perform the necessary Fourier transforms, the first aperture synthesis imaging telescopes were soon developed, which could obtain high-resolution images without the need of a giant parabolic reflector to perform the Fourier transform. This technique is now used in most radio astronomy observations. In 1995, these imaging techniques were demonstrated on an array of separate optical telescopes, for the first time allowing for further improvement in resolution. 2008, MIT professor Mark Tagmark and Matthias Zaldieraga proposed the first Fourier transform telescope, a design in which lenses and mirrors could be dispensed with altogether when computers became fast enough to perform all the necessary transform. And a view of the telescopes in space, quickly. We got the Hubble telescope in order for 19 years. It was one of the first NASA's great observatories, has revolutionized astronomy, studying images of countless cosmic objects and giving astronomers their most distant views of the universe with the Hubble Deep Field and the Ultra Deep Field. Hubble has shed light on the scale of the universe and life cycle of stars, black holes, and the formation of first galaxies. The Chandra, which we discussed briefly, was an X-ray telescope.
What was their view?
What was that?
5 stars, 4 stars?
What do you mean?
What's their view? Sorry.
It's okay. Go to your room.
You said you were going to review.
The third of NASA's 4 great telescopes, the Chandra, is the world's most powerful telescope, most powerful X-ray telescope. Chandra, named after the Indian-American physicist Subramanian Chandrasekhar, I did it, examines the X-rays emitted by some of the universe's strangest objects, including quasars, immense clouds of gas and dust, particles sucked into black holes. X-rays are produced when matter is heated to millions of degrees. Chandra has teamed up with several times with other telescopes, including Hubble, to take composite images of galaxies and other densities of the cosmos. We got the Spitzer telescope, launched in 2003, the last of the great telescopes to be launched, and gathers infrared radiation emanating from cosmic objects, including faraway galaxies, black holes, and even comets in our solar system. Infrared radiation is hard to observe on the ground because it is largely absorbed in the Earth's atmosphere. Spitzer was the first telescope to see light from an exoplanet, which is not originally designed to see. It took the temperatures of so-called hot Jupiters and found that not all of them are very hot. The Herschel Space Telescope, launched in 2009, lobbed into space on May 14th of that year, along with the Planck Telescope. Herschel is the largest and most powerful infrared telescope, looking at far infrared and 7-millimeter wavelengths of light generated by some of the coldest objects in space. It's also designed to look for water, which brings us to the Planck. The Plank Observatory, which was launched in 2009, is the Herschel partner, concentrating on the microwave light of the universe. Planck is looking for the remnants of first light to find freely in the universe, cosmic wave, microwave background. Planck is following the footsteps. It follows in the footsteps of the cosmic background is already coded. The Kepler mission, we don't have to talk too much about it, but it is found looking over at just a small portion of the sky, but it has located some 2,500 possible planets. A spectacular piece of equipment. We have the Fermi Gamma Ray Telescope that was formerly known as GLAST, G-L-A-S-T, joined the ranks of space telescopes in 2008. Best view of the most extreme energy cosmos gamma rays. Gamma rays can reveal some of the most energetic and mysterious events in the universe, including dark matter, black holes, and spinning pulsars. Swift Telescope is like the Fermi. The Swift scans the sky for gamma rays, specifically looking for gamma ray bursts, the most powerful explosions in the universe. That one was launched in 2004.
Are all things orbiting the Earth?
Yes, they are.
Not all are orbiting.
No, some of them are at the Lagrange point, some are, yeah, that's for sure. The European Space Agency in 2002 also put up the Gamma Ray Astrophysics Laboratory, its first observatory that can simultaneously observe objects in gamma rays, X-rays, and visible light. Integral, like Fermi and Swift, is tasked for looking for gamma ray bursts. The Newton XX1, moving to shorter wavelengths in the electromagnetic field. It was launched in 1999. The X-ray multi-mirror mission Newton, named obviously for ice cream. The X-rays also. Galax is the main mission of NASA's Galaxy Evolution Explorer, is to help better understand the formation of galaxies. It studies the shape, brightness, size, and distance of galaxies beyond the universe, beyond the known universe. Since its launch, Galax has imaged more than 500 million objects across 2/3 of the sky. And I think the last one is Cora. And Cora is, in 2006, it's down to the spectrum to the wavelengths humans can see. The Convention, Rotation, and Planetary Transit mission has 2 objectives: to search for extrasolar planets and also to orbit close to the sun and to conduct stellar seismology. And I think this is the SOHO, which is, I think, is the last one. No, there's one more after that. And while other telescopes are busy looking at distant stars, SOHO focuses on our own. So it's designed to study the structure and dynamics of the interior of the sun, as well as the solar wind stream of charged particles ejected from the sun's upper atmosphere. Understanding these solar phenomena is key to making better predictions of space weather, such as polar flares, which can affect electrical grids and communication networks on the Earth. To date, SOHO has taken first images of the sun's convection dome, known as the structure of sunspots below the sun's surface, and discovered new phenomena such as solar tornadoes. SOHO has also spotted 1,500 comets. And stereo was the last of them.
Sure. On the SOHO, isn't there a SOHO A and a SOHO B?
Well, actually, you have the LASCO on it as well, which also uses an occulting. Yes, there is. Another solar observatory, stereo, the Solar Terrestrial Relations Observatory. The mission is actually two separate spacecraft that, after launching, parts of the one trails the Earth and the other leads it. These positions allow for stereoscopic imaging of the sun and solar phenomena. It's taken 3 images of solar storms and coronal mass ejection. And this is the latest one which we talked about just briefly. India's polar satellite observer vehicle lifted off on September 28th. The PSLV C-30 mission included the launching of the Indian Space Observatory satellite, Astrosat. And that's our bibliography, and that is the story of space telescopes. Any questions real quickly, because we are out of time?
Is stereo B still dead?
Yeah, it's still working.
Wait, still working or still dead?
It's still dead. We had a problem, and yes, that's correct. Does anybody have any questions at all?
Are they gonna launch one to replace it, or what are they gonna do?
Yes, they are. That is the plan, but they need funding. We don't know whether they're going to get funding.
Right, your congressman.
Yes, that is. That's
We're gonna go around.
If they were a Planned Parenthood, they'd be able to do it.
I tried to run through this as fast as I could. I think it works.
All right.
All right.
Thank you, Ken. I have